Matrix multiplication. The product AB of a row matrix A and a column matrix B is a 1-by-1 matrix. The length of the row in A must match the length of the column in B for the product to be defined. To find the product, multiply each entry in A, going from left to right, by the corresponding entry in B, going from top to bottom, and then add the results. So for example, if we're going to multiply the row matrix 2, 4, 1 by the column matrix 2, 10, -1, we multiply 2 times 2 to give us 4, 4 times 10 to give us 40, and 1 times -1 to give us -1, and then we add 4 plus 40 plus -1. In our second example, we're going to multiply 2 times -3, and then we're going to multiply 1 by 1, and then we're going to add. So 2 times -3 is -6, plus 1 times 1 is 1, and so that sum is -5. Now, in general, the product of two matrices AB is obtained by taking the ijth entry to be the ith row of A times the jth column of B. Let's take a look at an example. We have a row matrix R, and then another matrix with 3 columns, C1, C2, and C3. Because we're multiplying a 1-by-4 matrix by a 4-by-3 matrix, our end result should be a 1-by-3 matrix. The first entry is going to be the row 2, 0, -1, 3 by column 1, 1, 1, 0, -3. Multiply the entries that correspond to each other, so 2 times 1, 0 times 1, 0 times -1, and 3 times -3, and that gives you -7. That's the entry in row 1, column 1 of our final matrix. Next, we take R1 and we multiply by C2. This will give us the entry in the first row, second column of our final matrix. So 2 times 1, 0 times -6, 5 times -1, and 3 times 8 gives us 21. Lastly, in row 1, column 3, we'll take R1 and multiply by C3. So 2 times -8, 0 times 0, -1 times 2, 3 times 1, add together to give you -15. Now we have two matrices that are both 2 by 2. Our end result is going to be 2 by 2. And we're going to start by multiplying row 1 by column 1. So 1 times 3 plus -1 times 5 gives -2, the entry in row 1, column 1. The entry in row 1, column 2 comes from multiplying row 1 in the first matrix by column 2 in the second matrix. 0 times 1 plus -1 times -1 is +1. Next, we'll multiply row 2, column 1. So 0 times 3 plus 2 times 5, which gives us 10. And now row 2 in the first matrix by column 2 in the second matrix. 0 times 0 plus -1 times 2 is -2. Here's another example. We've got our first matrix, that's 2 rows, 4 columns, multiplied by a matrix that's 4 rows, 3 columns. This should give us a matrix that's 2 rows and 3 columns. So we start by multiplying row 1 from the first matrix by column 1 in the second matrix. Then row 1 by column 2, then row 1 by column 3. When we do this, we end up with a matrix that looks like -4, 21, negative 21, 4, negative 5, negative 2. Here's another example. Our first matrix is 2 rows, 1 column. Our second matrix is 1 row, 2 columns. So our resultant matrix is going to be 2 rows, 2 columns. The first entry is row 1 from the first matrix times column 1 from the second matrix. So negative 3 times 2 is negative 6. Then row 1 of the first matrix by column 2 of the second matrix. That's negative 3 times 1, etc. The identity matrix is an n by n matrix that has ones down the main diagonal and zeros everywhere else. So the 1, 1 identity matrix is simply a 1. The 2, 2 identity matrix is going to have ones in the 1, 1 position and the 2, 2 position. These identity matrices are always square, and they have a lot of really, really nice properties. Well, here's a matrix A. We're going to compute A times the identity matrix and the identity matrix times A. Let's start with the identity matrix, A times the identity matrix. So here we go. I'm going to multiply row 1 in the first matrix by column 1 in the second matrix. So A times 1 plus B times 0 plus C times 0. So A. Then we're going to do row 1, column 2. So 0 times A, B times 1, C times 0. So B. And then we'll do row 1 times column 3. So A times 0 plus B times 0 plus C times 1, or C. If you follow this through and do all 9 entries, you'll see we end up with exactly the same matrix that we started with. In fact, the same is true when we multiply the identity matrix by A on the left. The identity matrix has a similar impact that's equivalent to multiplying something by 1. So here's some more properties that we should probably be aware of. If A, B, and C are matrices, and O is the 0 matrix, and if I is an identity matrix, then the following things are true. We have the associative and commutative laws for addition and subtraction. We can add the 0 matrix to any matrix without changing it. We can add a matrix to the negative itself to get the 0 matrix. We can take the sum of 2 matrices and multiply it by a constant, and that's the same thing as a constant times the first matrix plus a constant times the second matrix. And similarly, the sum of constants times a matrix is a constant times the matrix plus the second constant times the matrix. Similarly, we can multiply any matrix by 1 without changing it. Any matrix A times 0 is the 0 matrix. We have the associative law for matrices. A times B times C is the same as A times B times C. We also have that a constant times a matrix product is the same as a constant times the matrix times the second matrix. We have multiplicative associativity as well with constants. So C times dA is equal to CD times A. If we take a matrix A and multiply it by the identity matrix on either side, we end up with the same matrix A back. If we left multiply a sum of two matrices, so B plus C times A on the left, we get AB plus AC. Similarly, if we take a sum A plus B of two matrices and right multiply by C, we get AC plus BC. We also get multiplying any matrix A by the zero matrix is the zero matrix. Notice that we don't see that A times B is equal to B times A. This rule doesn't hold in general. And in fact, if we can multiply A times B, we don't necessarily know if we can multiply B times A. The dimensions might not work out properly. Regarding transposition, A plus B transpose is A transpose plus B transpose. C times A, the transpose of that is C times A transpose. And the transpose of AB is actually B transpose A transpose. So just take note of the last property. Here's an example. We want to take the transpose of the product of these two matrices. So let's first begin by taking the product of the two matrices. So in the 1, 1 entry, we're going to go 3 times 1 plus negative 1 times 5. So we get negative 2. Then 1 times 0, negative 1 times negative 1. So that gives us 1. Next, we'll go 0 times 3 plus 2 times 5. That gives us 10. And then 0 times 0 plus negative 1 times 2 is negative 2. So this gives us the product. We still have to take the transpose. So we take the transpose and we get 2, negative 2, 10 is the first row, and 1, negative 2 is the second row. Now, if instead we reversed the order and took the transposes first, we would end up with something that looks like the product of 3, 5, 0, negative 1 times 1, 0, negative 1, 2. And if we multiply those guys together, we get 3 times 1 plus 5 times negative 1, or negative 2, etc. So negative 2, 10, 1, negative 2. This example shows us that the transpose of AB is equal to B transpose A transpose.